Okay, start recording. So, during the last lecture, we taken a look on structures and on the preprocessor of C and C++, and today we'll complete our initial dive into C++ with a deep dive into function and function calls and so on. The rest that comes after it is then a bit higher level. So let's start. Create a new project for that, of course. Create new project, application, functions. Okay, so as you may have noticed, we already worked with one function, the main function, which our application starts. But now we will learn how we can call another function and how we can create own functions, which is extremely useful, obviously. So let's start with a very simple function. Let's call it my function. Let's give it 2 arguments. So we start with a return value. So every function in C can be defined such that it can return some value. How this return works will depend on the type of return value that we want to have. Also, it will depend on the calling convention. In other programming languages, there is a distinction between function and subroutines. Basically, the difference is a function has a return value, a subroutine does not. In C, everything is a function, but you can have functions that have a so-called void return type, which means they don't return anything. And this is, I think, a more reasonable approach. It really don't benefit from having like different syntax for function which returns something or nothing. So yeah, you start with the type, then you provide a function name. The name is constrained by the same constraints as a variable name, so it has to be made up of letters, small or large, underscore and numbers, and it cannot start with a number. It can start with an underscore though. And then you provide normal round brackets, and then within which you provide a list of arguments, which are defined quite the same way as you would define variables. For example, int my arg1, comma, and then the next int my arg2. So we have only 2 arguments, and then like with the main function, we provide a code block, a scope with this curly brackets, and everything that's inside will be the body of our function. So let's make the function do something simple. My write1 value is equals my argument 1 plus my argument 2, as simple as it gets. And then if we want to terminate the execution of a function, we use the return keyword, and then we provide the value which the function is to return. Would we have a function which does not return anything of type void, then we would have just return without something to return. Okay, so and now let's call our function. So we'll create 2 new variables, int my var1, let's say 1, 2, 3, and my var2. We have 4, 5, 6, and then let's int my return equals my function, comma, my var1 and my var2. So it's quite simple. Of course, we can use this anywhere. So if we want to do something with the return value of a function, then we write the name of the variable we want to assign the return value to, and then equals, then we call the function and provide the arguments in round brackets that are to be passed to the function. If we don't care for the return value, we just call the function directly. Even if the function has a return value, we can do that. It just means that the return value will be discarded once the call is completed. We can of course use functions also in equations. So in an if, in some loop, wherever we want, wherever we can write an equation, we can also use a function to do something. And whether a function inside an equation will be called or not will depend on the logical expressions that precede it. So as we have seen, if we use logical operators like the double or the double AND operator, or if we use the trinary operator, then the control flow already within the equation might flow around certain portions of said equation, so that unneeded calculations won't be executed. And this also applies if we have a function. So for example, if we would have something function and then or another function, then if the first function would return true, then the second function would not even be called. And then of course the whole expression can be still evaluated as a boolean, so we can use it in an if or in a loop as a condition. So let's put a breakpoint here and take a look how this looks. But before we run it, as usual, we need to disable a couple unneeded features that make the code less easy to understand. So we don't want this thing, and we don't want this thing. We don't want this thing. I think we just leave it empty. What else do we don't want? We don't want something in the linker. I think it's this one that creates a jump table that makes things more confusing. That should be enough. Let's run it and see what we see. Okay, that already looks simple enough. So I think we turned off enough things. Right. So as you see here, we move one of the values of our arguments into one register. The other, here it's not shown with the name, but it will correspond with var2 into the other register, and then we use the call opcode to jump to the function. Now let's see what exactly is happening, and later we'll also see how it works if we have, for example, more arguments than registers, because obviously we only have a limited amount of registers, so we can not rely on being always able to pass all the arguments in registers. And in fact, in the x86 calling convention, we only pass up to 4 arguments as in registers, and every other argument that comes afterwards is put on the stack. So we'll take a look on that next. But before we do that, let's look here. So we have here our registers. That's all we need for now. That's all we care for now. So the register gets its value assigned, the other register gets also its value assigned, and then the call will be executed. So when we use this function, we jump in here and we see, of course, two things changing. One is the instruction pointer, since it basically jumped to the function, kind of like a jump instruction, but it also changed the stack pointer. And we can inspect said stack pointer. So let me see where it's pointing to. Okay, and what we see here is that there is an address on the stack. So we could get the address. That helps us to do something helpful with that. And as you can see here, the address points to something inside the main function. It even tells us here the line, but that's only because the debugger has the debug database, so it knows which address corresponds to what. If we would not have a verbose debug information, it would only be able to tell us the function, and if you would have no debug information, it might not even be able to tell us the name of the function where this came from. But the way this works on a low level is that as soon as the call instruction is issued, the CPU writes at the address where RSP points to. The address of the next instruction after the function is done with, after the whole function call is completed. So if we see this here also in the call stack. So if we go back here, the address which it will be pointing to will be pretty much the next address. Should be this one. Let's see, registers, not registers, in Windows. So 4500181. Yeah, this and this are identical. So we have put on the stack the address of the next thing to do once we are done with the function. So now let's keep this in mind, but return to our function. So as you see here, it's not very complicated. First thing it does is it saves those two registers in which it got its two arguments to the stack, two offsets of the stack which already has been pre-allocated by the calling function. This is called the scratch space, and it's only available in the x86, well, generally in modern 64-bit calling conventions. It's not available in the 32-bit calling convention. That one works quite different. We might take a look on the quaint calling conventions sometime later. For now, it's just important to know that on modern 64-bit systems, you just have one calling convention for all the function calls. And when I say calling convention, what this means is pretty much how the arguments are passed, which registers are used in which order, basically everything that is not strictly enforced by the hardware. So by the hardware itself knows only the call instruction, and then the other instruction return here, with which you return from the function, and those handle putting the address on the stack and then reading the address back and jumping to that address. But everything else with regard to return parameters, which registers to use, how to lay out the stack, etc., those things are pretty much up to the developers of the software to define how they want this to work. So for example, calling conventions on Windows and on Linux work to some extent differently. They just decided that they like it to do it in a different way. With ARM64, the thing is a bit different there. For interoperability and in order not to reinvent the wheel, usually everyone that uses ARM is just sticking to the calling convention as recommended by the ARM company that designed the CPU architecture. Although that said, for example, on Windows, on ARM, when you are using the emulation layer of Windows, it will basically simulate a x64 calling convention with the ARM registers. So it kind of will be slightly less efficient since ARM has much more registers, but that shows very clearly that such a calling convention is at best a recommendation. Of course, all your software which needs to work together needs to use the same calling convention. If you have a library which uses a different calling convention than your main application, that will cause a crash or at least some unpredicted behavior. So while it's technically free to use, and if you write your own assembler code, you can invent whatever calling conventions you want within what the hardware permits. There are some mild restraints with regard, for example, to the stack alignment on the x86 platform. So with regard at which offsets values on the stack can begin, you cannot put it like at offset 3, but you need to have a 16-byte stack alignment when you execute the call instruction. But this is like a very small constraint in the bigger scope of function calling conventions. So yeah, you can do whatever you want in your own assembler code, but as soon as you are calling some functions of some other libraries or some functions of the operating system, you need to stick to the default calling conventions. And at least the Microsoft Visual C compiler on x86 will only support the one calling convention that we have here. And if you are building on ARM, then it also is then capable of creating this hybrid calling convention that is used by the emulation enabled binaries. Okay, so as said, we copy the data here, then we save the old RBP register. This is also a thing which is defined in the calling convention, which registers are so-called volatile, meaning after the function was called, their content might be whatever, and which are well, non-volatile, which means if your function is going to change this register, it must change it back to its original value, because the function which calls your function relies, or at least might rely on, is allowed to rely on, let's say it like this, to assume that whatever it put, for example, in the RBP register, it will still be there after the called function was done with its own execution. And in this case here, even this simple function, it backups the RBP register, and then it moves the stack pointer by 50 hex, and then copies the stack pointer to the RBP register, and then it does its own internal logic. So in this case, we load the two arguments, we do the add, remove it unnecessarily, and then we save the value to to our own memory, which we have here in our own allocated on our own stack within this, on our own stack frame within this function. So the terminology is like this: you have, for every thread that runs on your system has a stack, and every function that is called creates an own stack frame, and this stack frame contains everything that the function wants to work with. It must be as large as the function needs it to be, and when the function is done with that, the data there become invalid. Usually the RBP register is used as a base pointer to point to the begin of this stack frame, but this is not something that is mandated. So if you have a debug build like here, you will see that the compiler will be using the RBP register for this purpose, and using it like this helps a lot with stack walking. So basically what we see here, that we can easily find functions which call the other functions and so on, because we just go to the we check basically on the stack. We have this we know where these base pointer frames are put, and then we can look them up, and then from there we can look up the next one and the next one and the next one. And however the compiler does, if you make a release build, since there is no utility in having this base pointer used as a stack frame other than for debugging, so for the execution of your program this has no utility. So often the compiler in release builds will use this RBP register for other internal purposes, making the stack traces not necessarily as easy to perform as it would be otherwise. The Visual Studio Debugger is quite good in working even under these conditions, but this is just something to keep in mind, that this layout with the base pointer is rather something that you will only see in the debug build. That said, if you are writing some own assembler code, it is quite handy to have this base pointer at hand, just for your own assembly code, and to easier be able to visualize which addresses you want, which offsets you need, and so on. The compiler, since it has infinite memory and is quite smart, can just use the RSP pointer plus whatever offset, and then just keep track in its own Scratch book about all of these addresses that are then used. And of course, each time such C code is compiled, it redoes this from scratch anyways. While if you would have some assembly code, you would want it to write such that if you have to change it in some way, you don't need to rewrite all of it, because that would be a huge waste of time. So that's why initially this RBP pointer as a stack frame base pointer was introduced in the past and used a lot when people wrote their assembly code by hand. Nowadays it's just there for easier debugging, and otherwise it can be repurposed for other things. Okay, so we have here our addition. Then here we have our return instruction. So what it does when we call return, it will, in case of machine types, save the return value to the rex or EAX register, and then it will unroll all the changes that it made to the stack and to the registers, except for the volatile ones, and return. So in this case, we wrote the original RSP register, which was before we started modifying it, and then we use the pop. So push basically takes a value from a register, puts it on a stack, and advances the stack pointer. Pop does the opposite. It takes a value where the stack pointer points to, it puts it in a register, and it de-advances, let's say, at the stack by one slot. And then we have the ret instruction, which will take a value from the stack and then just jump to it. And of course, in the same go, de-advance the stack pointer by one slot. So we can put a breakpoint here, because that's what will be interesting. And then we can see, okay, we have some return value in our rex register. We don't care for the others. We have the instruction pointer, which is still pointing to here. We have the stack pointer, which here within the internal execution, since our last breakpoint did not change, or it changed and was changed back. So as you see, generally in this watch windows and the register window, everything that changed from one step to the next is shown in red, so that you see what changes and one didn't, so that's quite nice. And when we execute this ret instruction, we see that the instruction pointer, of course, now points up to here, and the stack pointer was incremented by 8 bytes. So yeah, and then we are of course here, and then can continue the execution of our function normally. An important thing to keep in mind with the stack is that the way it grows is when we look back into or look here, is that you subtract from the so like it grows from the bottom up. So you have some addresses, and you have high addresses which are valid, and if you need more space, you pretty much decrement the stack pointer, and then you have some more space. The way this works under the hood is that you already have a significant size of stack space allocated for by the operating system for your thread, and then within this space you can just address pretty much any address. So you don't need to actually do any memory allocation. You just select a new address, like here with subtracting a value from a register, and then you can use it directly. And of course, if you would have a function which needs more space than is allocated, the mechanism for this is that after the usable space is some space which is marked by the CPU such that if an read or write access to this space happens, a special type of exception is triggered, and then the operating system can allocate in this place new pages, new memory space basically, and then it tells the CPU to resume the execution where the exception happened. So the last instruction, which caused the exception, is then retried, and then this memory is then available automatically, let's call it, and then
could we maybe take a small step back and
yes?
You could repeat what exactly is this stack? Is that just some range in the memory that we call the stack, or what is it physically?
Physically, it is a range in memory which has been selected by the operating system at the time when the thread was created, and the whole memory range was dedicated to the stack based on the maximum size that was specified that the stack can grow to. But physically, only a small portion of real system memory has been committed to this memory range. The rest of the memory range does not correspond to any physical memory which exists in the system yet. And memory generally, when it's managed, it is managed in so-called pages. On modern systems, a page is 4 kilobyte. On very modern systems, like some ARM-based systems, like the newest Macs or also Raspberry Pi systems, a page is 16 kilobyte. And this is pretty much the granularity with which the memory management unit of the CPU can manage permissions with regard to memory, and of course also memory mapping. So this will be actually the next subject which we will talk about, memory management, but I can maybe already tell you now a little bit about it. So the memory address space that your application has is not related to the physical address space of the physical RAM which is installed in your system. There are so-called page tables which contain translation information from your virtual address space to the physical address space. So the operating system can take any page in the physical memory and put it at any address of your virtual address space. So you can have, for example, two applications running on your system, and they can, if the operating system chooses so, both have the same physical memory page accessible within their memory address range, but this can be at completely different virtual addresses. Okay, and with the stack, the way this is done is that some starting address within the available not yet used address space of your application is selected. Then a few pages are committed to this range, and after this is a so-called guard page placed. So a page entry in the paging table which tells the CPU to raise a very specific type of exception if a read or write access to this page occurs. And then you are just using your however many pages you have right now, and when you call a function which calls another function, at some point you call so many functions that the function will want to write to some address which will lie within this guard page, and this will trigger an exception. And at this moment, the operating system's kernel will be invoked. It will see, aha, this was this type of exception, so everything's fine. Let's find some free memory block in the physical memory, map it to this page, and then instruct the CPU to retry the last operation which previously failed. And when the CPU then retries the operation, since now there is an entry in the page table which actually points to a real physical page of memory, the read or write operation succeeds, and the whole story gets repeated with the next page that needs to be allocated. In reasonable implementations, the CPU, the kernel of the operating system would probably not just allocate one page; it would just allocate some amount of pages which it deems reasonable based on available memory or on the size of the already existing size of the stack, etc. Does this answer the question?
So everything regarding my application is saved within the stack, and then
no, everything regarding local variables or functions within each thread of your application.
And then as it goes on, if needed, the stack gets extended.
Exactly.
Okay.
And when you have an application and you want to have some variables, some data, which are not local variables to one of your functions, which is a very common use case, you're using a memory concept called a heap, and this is implemented quite in a complicated way. So the Windows API on a high level already offers you a built-in application heap. So you call a function which will then just request an arbitrary amount of memory, and this memory will then exist somewhere within the address space of your application, completely independent from any thread or any function. And this this memory can then be accessed by multiple threads at the same time. Of course, then you need to synchronize it somehow such that you don't overwrite data which were just written or things like that. We will come to this later on. The only thing here to say is that that the way this is implemented requires communication from this heap implementation with the operating system kernel, because the application itself, it cannot allocate memory in reality. The application itself can only ask the operating system, hey, could you allocate some memory for me? And the way this is implemented, it could even say, I would like to have this memory at address such and such, and the operating system will then either success or fail this request. And then the heap manager within the application will get a reasonably large chunk of memory, like 64 kilobytes or a few megabytes, depending on the implementation. And then when your application, your code, like wants a small chunk, it will just from the pool that it got, select something empty and give it to you. And at this point, the operating system doesn't even care about the details here, because you have a much larger block and the operating system cares only about this large-scale picture. This improves the performance a lot, since any interaction with the operating system kernel is quite slow in comparison to local function calls. Okay, shall we continue? Good. So, where were we? Right. So we were here, we had return, and then yeah, and pretty much that's it. The last instruction that we have here to execute is to take the value from EAX, so our return value, and put it into some memory on our stack. Okay, so let's now take a look how what else we can do. So first of all, we can have pointers to functions. So this is like with pointers to variables. Any pointer is just an address. Every function is just an address as well. So we can have obviously a pointer to a function. The way those are defined is a bit less pretty. We have the return type, then we open round brackets instantly. Asterisk then we write the name of the pointer, and then we write the calling convention for the pointer. So the pointer, when it's defined, needs to know which arguments the function will expect. Otherwise, it cannot be used. And when assigning a function to a pointer, it's like with assigning an array. You you can just do it directly. You don't need the add operator or anything. And while with the and here I think if you would add the add operator, that would just ignore it and not actually even fail, but it would not be correct. Just assign it directly. And then the nice thing is that you can call such a function by a pointer the same way as you would call a normal function. So there is no need for some dereferencing operator asterisk or something, because just the use of the round brackets implicates that you are calling this thing, and the compiler knows whether this thing is a function pointer or whether this thing is a function directly, so it will know which code to generate. The code, of course, will look slightly different than for a normal function call, so we can put a breakpoint here and take a look again. So if we compare this portion with this portion, we see that it is quite similar, just that here we have a call. Basically, if we disable the function names, we just have here a call to an address, and the address was determined while the compiler compiled the code, while here we have a call to a on a pointer. So we have the base pointer plus 10, that this is where the address of our function lies, and call does this in one go. So as we see here, the call instruction, the call opcode can actually contain more than just a few internal operations for the CPU. On ARM64, you would need to first explicitly load the address from memory to a register, and then you could call that register. So like with everything on ARM, you usually need much more code to do the same thing, but as long as the compiler generates the code for you, it doesn't matter. The main advantages of this complex instruction sets are like the x86 64 instruction set were that they were quite nice for people that wrote assembler code by hand, to not to have to write too much code to achieve their goals. But with modern approaches with compilers, that's completely a non-concern nowadays. Okay, so let's now take a look how this would look if we want to for example, pass a structure. So as we know, a structure will not fit into a register. And as I told you initially already, the first 4 arguments are usually passed in registers on x86. So how would that work if we define some struct? Let's define it somewhere, maybe here. Struct, my struct int var1 through 5 or so, 2, 3, 4, 5, 1 too much, semicolon. That's 20 bytes. Just write it down so that we don't forget it, and then let's write a function. So int my function s for structure. We'll give it the same arguments as we had before, and a third one. Okay. So and now we will do it in a first. We do it in a simple way. So my struct that to be lowercase. My struct my arg3 non-capital A, and here let's what do we want to do it we can just assign something, or we just let's just copy this and add a few more lines of adding things. Plus my arg3 punct value 1, value 2, and value 3. Okay, and to illustrate something that we will see later, let's assign 4 and 5 with some values. Let's say 7, 8, 9, and for 5 we'll assign just arg1. Okay, good. So we define our structure, and we could in principle initialize it with zeros. We don't really need there to be anything interesting. My class is equals 0. We could of course initialize it with more arguments, but that doesn't make a difference. So we have here function s. We will use the same arguments we used before, just that we add the third argument. Suck. Okay, we put a breakpoint here. Also, we want to capture the return value, so let's do this and let's run it. Okay, so before we step through it, let's just step over it and see what happens. So we got a return value. Our arguments are unchanged, so as we see here, they are all zeros, even though we had here some assignment done, which was completely for nothing. But we'll see later how we can make this propagate. Okay, so we run again. Okay, so what we see here is, okay, we have our so we load a few addresses. We load a few values, so RCX the first, RDX, then we have here, as you remember from assigning structures, we set up here a copy operation. And what we basically do here is we create a copy of our myvars, just one which is not kind of visible here in the C code. And then once we are done with this, so we are copying to destination is RAX, so RAX will contain the address of our copy. So actually, maybe for funsies, let's actually add some values here. 0x AA DB CC, oops, 0x D and 0x EE, too many E's. Okay, that looks nicer this way. Because the spaces are meaningless, it's just for the reader to have it look nicer. So let's grab the. So first we load this into address A. So we step over this. Now we have an address in RAX. So let's go to memory in RAX. Add a few more steps. Okay, now we put a breakpoint here after we are done. We run it. This. So we have here AA, CC, where's the rest? PB, DD, EE. So it has copied the data. You can again re-enter the RAX. It didn't change, so we have the right offset. It copied them here, and now we load R8 with the same address as we see here. So the registers which are used in the calling convention are RCX, RDX, R8, and R9. So R8 is our third argument, and then here of course we RDX, we don't need that. RCX, RDX, we don't need that. These are these two arguments that we have filled before. So as you see here, also the order how the arguments usually are handled is like from back to front, and not from front to back. And then we have our function call, and inside the function, so we have seen that actually what is passed in the third argument is not the structure, since this doesn't fit into a register, but instead the address in memory of where this whole structure lies. So basically we are passing a pointer to a copy, and then inside our function here we can just address this copy and do things with it. So we won't step through that, that will not be interesting. And then when we return from our function, then then we are basically done, and we can just save our return value and unwind everything. The compiler generally will just allocate one large stack amount, or well, not allocate but reserve a large stack amount, and then just use it and offsets within it. So it's not always very directly clear what is used where. If you would write such a function call manually, then you would usually reserve the stack before the function call and then unreserve it after the function call. But this of course kind of adds unnecessary overhead, since it's much easier to just reserve a bigger chunk at the beginning and just unreserve everything in one go at the end, since then you save on instructions. You just need instead to keep track of all the offsets that we are using, and for the compiler this of course is quite trivial. So the other way how we can use a structure is we can pass it by reference. So like with variables, as you remember from our pointer class, you can have a pointer, of course, to variable, but you also can have a reference, which effectively makes the variable, while it behaves like a local variable, it's actually a pointer, and if you assign something to it, the assignment will be done on the original variable, the internal references. So if we do it here, just add the AND operator, and run it again. No, let's run it again. We need to change the name. RSR, let's call it, for reference, and then let's didn't take the RSR. Okay, and then let's make another function call to our function descended by reference. So as you see, whether a variable is passed by reference or by value is decided by the function definition and not by how we invoke the function. In other languages that might not necessarily be this way, but in C++ this works like this. And here, of course, we now see that the call is much simpler, because we just put the address of our already allocated mystruct into R8, then we put the two other arguments into RCX, RDX, and we are happy, and we can do the call. And now the last variation on this, of course, is to use a actual pointer, which on the technical side is kind of irrelevant, doesn't make any differences, but of course on the practical side you see that now the code doesn't compile, because we need to replace the dot operator with the arrow operator everywhere where we are using this pointer. Oh, and what I of course forgot to show you, but assume that would be obvious, is that after that, for this function and for this function, obviously any change to the reference or pointed to variable will be reflected in the calling function. So before I add a call to the other thing, we can just see here. So we are here. Our var contains, let's enable hex display, contains a, b, b, c, c, d, d, e, and once we step over it, so the function gets executed, the two lower ones are changed to whatever we had there assigned there inside our function. So this already gives you a tool on your hand what to do if you would want to return more than one parameter, because obviously since you only have like one RAX register in which you can only return one value, and for equations a function is supposed to have one return value, roughly speaking. In a practical sense, when programming, you might want to have like 10 return values. You might have a function which will return you the file size, the file date, and something and something and something. There are of course ways how you can achieve this only with technically one return value, but a very nice and commonly used way is to use this reference. And of course, if you want to ensure that you cannot modify whatever is passed, so if you don't want to use it as return value, you can just write const, and then the compiler will just not allow you to modify it. Of course, you could then cast it back to non-constant and still modify the value, but that's not what's intended. So, and of course, the advantage of using such a by reference argument instead of passing such a complex argument by value is that if you pass it by const reference, then it's much faster. Just one instruction instead of like 4 or 5 instructions, and one which is a rep instruction, meaning it will be repeated multiple times until the whole block is copied. So this is quite an efficient optimization wherever you can. If you have non-simple machine types, then don't pass things by value, but just pass them as a const reference. This is safe enough, and it will really save on computation. Now with pointers, of course, you could also pass a const pointer, which would then of course not allow you to assign things to it. And we of course need here a different name, so let's call structure and pointer sp. The nice thing is of course that the usage with the pointer, here of course the compiler complains because this is not a pointer, so we need to dereference it. But when we compare the code now, it will actually look identical. So as you see, this call and that call, they are identical, and the ways the functions are internally implemented will also be the exact same. So even though the code is written differently because here you use this arrow operator while here you use the dot operator and so on, functionally both codes are identical, because as I said already during the lecture about pointers, effectively a pointer and a reference is the exact same thing hardware wise, it just looks different in code. And these references are in some ways more convenient to use. They make a more pretty code because you need to write asterisk something if you want to assign a value, etc. But functionally, it's a distinction without a difference. Okay, good. And of course, the next thing would be, what if we want to return something, like return a structure as a return value? So can we even do that? And yes, of course we can. It will, although, be implemented in a slightly different way than we might expect it. So let's be lazy and copy this here. Let's call it function s, I don't know, sx. And then of course we want to return it, so we to first define it, or should we define differently? Define it my red. We can start with 0. Then we just need to assign it here. Punct. Let's say variable 1 is this, and we can of course assign the others as well. So let's say 2 gets a copy of the first argument, 3 gets a copy of the second argument, and the other ones we just leave at 0. Or maybe we can even be fancy and say that the fourth one will be, oops, I press C, will be the difference. Whatever. Semicolon. Okay, and so let's see how this works. So we need to have another copy of our, actually we can reuse this structure here, we don't need to redefine it. My vars is equals, oops, I could have copied more at one go. Okay. Okay, so let's run it and let's see what it does. So, and show names. Okay, so var2. So we see that here we set up. Okay, I think this is not quite right because var2 should be in RCX. So the names are not correctly displayed. So let's just not show the names. So we move. No, sorry, it's fine. RDX, RCX, let's see. So the way this works is it takes the address of our variable and passes the address as the first argument. Is this not enough to display? So RCX should be the first address, and here, yeah, that is fine. The variable doesn't have a name yet because it's just a temporary variable. So it's basically doing a struct something here before, just we don't see it, and then this new struct lies at RBP plus 88 hex, and this address is passed as the first argument, and all the other arguments like this one and this one are then shifted by one slot back. So our var1, which for some reason doesn't get a name, it didn't get a name here either, lives not in in ECX, but now it lives in EDX. And our var2, which gets a name which previously lived in EDX, is moved to R8. And the D suffix just indicates that it's a double word size, so that the high 4 bytes are to be zeroed during the move operation. So the register as such is called just R8, and here when we see on the registers again we see the actual full names of the registers. If we use EAX, then it's, as already mentioned, just 32-bit, and with the higher registers we add a D at the back instead. Okay, so everything got just shifted. Then let's see what the function will do. So I mean, we can already expect what the function will do once we step into it. It will just write to the address. It will always grab the address and then write to it at the right offset, the same way as it would work with the other references here, just that it's kind of hidden from us and shifted. Okay, so let's go back to our function, and once we are done with the yeah, we need to go out of there. Once we're done with the execution, here we load an address into the RCX, the address of our of the destination. So here it should actually show the name of my vars, but it doesn't. then it moves it to RDX, so D is the destination, S is the source. Rex, and one more thing, which maybe I will rerun it, which I didn't tell, but it is not quite insignificant, is that once we are inside the function, and at the end, before we do ret, here we put the address of where the return value will, where the return value is supposed to live on the RAX register. So what before, the value which we have, okay, let's rerun this and write the value down just for correctness. So I want to run until here. So we have our value in the RCX register, intermediate, clear. So this will be the address. Oops, this is not enough. No, it doesn't tell us the. It just points somewhere, so it doesn't tell us the name of the function. But let's write it down. We can take a look there. It's currently just filled with some garbage. So once we then go into the function, and then go to here, so that the REX was executed, it should give us the same address as we see here, then as a return value. So it kind of obtained the address of a memory on the stack of the calling function, which it can use for the return value, and then for it's defined in the calling conventions. We could of course have a method where we say we don't get the address back from the function, we have to remember it, which would be just as fine. So this is just a artifact of how the calling convention is defined, and you know, having to remember less is always convenient. So we could here, instead of using RAX, have had this such a move, well, a layer with the, not move, but a layer with that word malware and so on, where we would then just load it. But here we just take the source pointer from the REX register, and then we of course set the size, and then we copy everything out such that in the actual variable where we want this to have to end up, where we want this to end up, the data will actually end up. And as it looks, actually we have even a second temporary variable generated, because it makes a copy operation yet again, just with different addresses, and this time the destination is here our myvar. So actually the first thing here was just to copy it somewhere else, and then it copies it where it should be. So obviously in a release build that would be much more optimized. For example, it could pick the address of this variable and pass it directly, so that the function writes to it directly, although only to a certain extent, because the way you might want this to work is that you actually do not modify the return value unless your function actually finishes successfully. So the way this works is, of course, functions can fail and throw an exception, and then in a more complex scenario you might not want some variable that was passed as argument to be partially modified. Exception handling we will also take a look at later. Yeah. Okay, so this is how you return a structure, simply by working with pointers and copying memory blocks around. So you see also that this is kind of inefficient. Even in the more efficient, more optimized ways, it would probably always maintain at least one copy operation. We can actually here make this be meaningful and try to compile a release build and then see how much optimized that would be. Okay, it needs to load a few libraries. Okay. Oh well. That's boring. It kind of removed all the code. It optimized too much. It kind of just performed the calculations and then just writes the one value it knows that this will always result in as a result value. well, we can use, since we already know how to call functions, we can actually call a function which will give us a random number. So hash include std, I think it should be in the std library. Int my rand, yeah. So the rand function just gives us a random number, although it's like really not really random. So on in computers, getting something really random is really hard. So what this thing does is it just has a algorithm which is fed with a seed value, and then it just reprocesses the same bytes and gets something that looks random as an output each time. But it's not really random. If you know the seed value, then you will always reproduce the exact same sequence of pseudo-random numbers that you got. There is a function srand which allows you to set the seed for the random number generator, which we won't use here, so we will really get the same rand each time. But I hope the thing will not be aggressive enough in its optimization to actually remove that. Yeah, this is meh. It still just took the random number and then just did the add. So I think we cannot trick the optimizer here. Of course, we could just disable the optimizer. That's also something we can do in C++, code generation, optimization. But if we disable this too much, it will not let's try to just disable it. What code it will then generate? If it will be at least somewhat more optimized. Now, if we disable the optimizer that much, it just generates the same code we already saw before. So we will need to have a much more complex real-life use case if we really want to see how the code could be optimized in a way which does not just gets rid of everything. So let's undo these changes here. This also changes like from Visual Studio version to Visual Studio version. Like on older versions, it was by far not as aggressive with the optimization. So with older versions, this time actually would have worked. It just needs to be old enough. Okay, so we had here our return values with a structure. We can implement, for example, a real-life use case where we would want to return a second parameter, as I already quickly showed here. Not in full detail. So for example, let's implement int my divide. It will take 2 arguments and a additional return parameter. So we can use this and also of course with integers. It is not restricted to structures. This works with everything. And here we just int my height, as we already had this. Oops, int is equals my arg1 divided by my arg2. But as the third argument, we want to get back the modulo. So this equals my arg1 modulo my arg2, and the other one needs to be returned, and a semicolon, and here. So that's one way, and the other way you can implement the same thing. Let's comment this out. Usually the more elegant ways is to use actually the pointer, because this gives us the flexibility if we actually want to use it. So we check if the pointer is set, and then we use the referentiation operator to assign the value. So now we can call the function my height is equals divide 1 2, and we can, okay, we need another integer. Let's call it var3. Doesn't really matter which value, the value will be overwritten anyways. And now if we run this, we will just get our okay, it's 0, so that's not a good example. Then let's switch the order of operations. Well, not of operation, just the order of division. Let's divide the bigger thing with the smaller thing so that it's not so boring. Okay, so we get here some value, and then here we get as the residual of the operation. And the nice thing about using this instead of a reference, if we don't care for this value, we can just write null, and then it will still work. We will still get our return value, but when we go inside here, this if would fail and this code would not be executed. So we save some time, we save some memory. So generally when you have return parameters of which you think that they might be optional, use a pointer. Only if you have return parameters where you say the call you will need that, definitely then it's reasonable to use a reference instead. Okay, good. So this match to that. Let's see what's next. Yeah, let's maybe write this down so that you can have both. And oops. And let's move this here, and let's not initialize it since it will be overwritten anyways. Okay. So now let's take a look how this would look if we would have much more arguments. So we just copy the function here, paste it here, and then we will have to copy paste a lot. So 3, 4, 5, 6, 7, 8, 9, 10, 0, 9, 8, 7, 6, 5, 4, 3. Okay. Let's not be too lazy. Let's so 3, 4, 5, 6, 7, 8, 9, 10, 9, 8, 7, 6, 5. Oh, I've missed one. 4, 3. Okay. And now of course we need to call it. So ret, not rat. And of course, as you see here, you don't need to use variables. As you already saw here, you can just use literals instead as well. And of course, keep in mind null evaluates to really just 0, 0. So you could write just null, or a very modern way of writing it would be null ptr, which is well, it's a modern way, so I recommend you using it, since it really gives you a real differentiation between the null as a number and the null as a null pointer. It doesn't make the differentiation on the hardware level, but at least for the compiler it makes it more clear what you want, and then the compiler can easier find potential issues and trigger warnings and so on. And of course here we are just using the normal literals to just feed in some arguments. We can of course mix them, as we see here, literals with variables. We could also actually call another function here as an argument, so we could have here something like that. Whatever we want goes, but these complex things we'll take a look at later. Let's just take a look on this. So as you see here, as I said, the first 4 arguments, if we have space for 4, if we have a return value which is a structure, then it will be only the first 3 live on in the registers, and then the other ones are put on the stack at defined offset. So the stack pointer plus 20 hex has the 5th argument, 28 hex 6th, 7th, and so on. And you can this way use as many arguments as you want. And let's now write down the RSP. Clear here. Actually, we could also open a notepad since we want to note a few things. This is the good old classic notepad, since the modern one is not really useful for editing config files and writing code. It's like more for writing grocery lists, so I don't like the new notepad. Anyhow, so we have here our RSP register, and we know that for example the 5th address lives at RSP plus this, so this here is the 5th, and the 6th argument is then of course plus 28, so it's actually quite easy to write all of them down. 6, 7, 8, 9, 10. Oops, 10. So this is 8, this is 8, 0, 8, 8, 9, 0, 9, 8, 9, 8, 5th, 6, 7, 8, 9, and the 10th, which we just call with 0. And let's just quickly check if I did not miscalculate anything. Yeah, 9.8. Then here we have, well, nothing. Those go in registers. And then we have our call. So let's do that. Yep. So let's put a breakpoint here and just jump to it so that we don't have to press the single step button too often. Let's go inside. And what we see here inside the function is that the first thing the function does is it writes to further addresses of the RSP and it saves this 4 registers to the stack. So here we have this address. It's then the fourth, or which one is it? Yeah, RDX, fourth argument, and then of course the same way, then 3, 2, 1, so 6, 0, 5, 8, 5, 0. So what basically happens is that we get a consecutive range of memory which contains all of our arguments, which will be needed in a second. Here, this is obviously like always done this way because that's how the function should work, and the debug builds always try to do things by the book instead of optimizing. The practical side is of course that you don't need to do that. If you know what you are going to do, for example here, further down, we actually then read those addresses, those values again from the stack for our operation, which would be completely unnecessary. We could just add ECX, EDX, R9 and R8, sorry, R8 and R9, and then only read the stack for the other ones. That would give us the exact same result, and that's how the code would be if the compiler would generate it with optimizations. We could actually try this by feeding just 10 rand calls to it and see what comes out with the release build. But here in the debug build, of course, it always does this obsolete operations. And of course, one more thing to now keep in mind is that if we go to the other side here, we had like plus 20, and that was the fifth one, and here we have plus 20, and that's already the fourth one. And the reason is because the value of RSP has been changed by 8 during the it was decreased by 8 to be precise by the call instruction, since at where the RSP was pointing before, the return address was put. So wait, 6, 5, this was need to be 8. So 6, 8, 6, 5, 8, 5, 8, 5, 0, and then we have here 4, 8, 4, 8, which contains the return address. At least according to our calculation. Let's see. Void asterisk asterisk. Yeah. So this thing points to function mainline 111 something something, which looks plausible. So that's how the memory gets structured, and as you see, you can really use any amount of parameters, as many as you want. That works just fine. Okay, let's stop it. And now, before we take, so there are two things which I need to show you about functions. Now, one is calling functions with a undefined amount of parameters, which you can do. And the second one is how it works if you use doubles or some things which need other registers. So I think first we'll do the variable argument functions, and then we go kind of to the more simpler things back to the different register types. Because this, I think, is the most pedagogically valuable approach. But before we do that, of course, we wanted to do this call with a lot of rand calls, and then try to inspect the... Alright, and we need to return it so that the compiler doesn't say that the whole function is pointless. Oops. Right, we need more runs so that we see how it optimizes. Breakpoint, debug, release build, run. Wait, we disabled the optimizer. We need to re-enable it for this, of course. Inherit from the defaults. Okay, run. Okay, so obviously, as you see, we have a lot of calls. So it calls the implementation of rand, and then it puts the things where they should go. So it puts them in here a bunch of registers, and then it saves them. Where's our final call? With rand, doesn't it do the final call? We should have added them together. We do. We return the value. Then we want to return the value at the end. Great. It inlined the function, meaning it just took it from here and put it there so that it doesn't need to do the function call. Well, as the optimizer, that's of course as annoying because we want to see the function call. Yeah, the optimizer is something to always fight with. Red 2, and we'll return with 1 plus that. So now that we are using the function 2 times, it should not consider it beneficial to inline it. Why did it? It's still inline it, rand, then it does this. No, it's still inline the function. Okay, let's try to select. But favor speech should let's try that optimization. Maybe we can find one which will no, that's not a good idea. Favoring speed is not a good idea. We should favor size of the application. Then it will not inline functions. Favor size. Because then obviously it doesn't want. But it's still inlined it. Darn, that's annoying. If I make a loop, of course it will do the same thing. It will decide that it will just inline it inside the loop, so that will not help us at all. I can just try to repeat that like a couple of more times at some point. It should decide that it's more efficient to not inline the function. 3, 4. No, it's just really okay. There is a keyword called underscore inline to force things to be inline, but I don't think there is like a no inline. Yeah, there is none. Okay, so unfortunately we cannot take a look on this in this simple demonstration case either. But at least we have seen another strategy of the compiler how to optimize code by inlining it. Can I somehow trick this thing to... No, not really. Yeah, wurscht. Then we won't see that anyway. So let's continue with the other thing, the variable argument functions. So there might be a use case where you might have a function and for whatever reason you don't know yet how many arguments you want. Excuse me. And you don't know how many arguments you want to pass to a function. So of course start with some standard function definition. Add some names so that we don't have a double. And basically to tell that you have an unknown amount of arguments, you can just use directly this 3 dots. But usually you would want to somehow be able to tell within the functions how many they will be. So usually when you make a function with a variable argument count, then not because you don't know how many arguments it will have, but because you know that in one place it will have 5 and in another place it will have 6 and in another place it might have none. So you want to make something that can take whatever many arguments you see fit at this point in time. And a very common way of doing it is to first use some non-variable argument that you will always provide, which will, in the simplest case, for example, contain the count of arguments. So int n args, and then you know at least how many they are. And an example of such a function, which you already have seen me, I think, using in the past, is the printf function, which prints things to the console. But we'll take a look into that a bit later. So this so obviously you could here, instead of just a number, maybe have a actual some complex structure that will inform the function which other arguments to expect. So this is as flexible as you want to do it. The only important thing here at this level is simply the handling of these 3 dots. And for this we will need a include, which provides a few important templates. So hash include std oops, std that should be all we need at this point. And then there is a defined data type for this argument list, which we can use. var list. Let's call it args. And then we need to initialize it. var start. And the way this works is we pass to it the list, which is supposed to be the list, and the first argument that we have at our disposal, so that it can know from where to start. And then we should of course semicolon it, and then here we can do something with it. So for example, we want to get the first argument, so int temp is equals var arg. Then we provide this pointer here, and we need to specify the type, and we have to know the type somehow. So how we find out the type is is up to us. For example, here we can define that this function, let's say it takes an arbitrary amount of numbers and then adds them all together, and they are always integers. So that's how we know, because we have defined it like this. There are of course more complex cases, as said, where you can have dynamically switch between types and so on. So here, let's make a loop so that we can loop through all the arguments. Int e. So then we want as next the second argument, comma in semicolon. E is less equals n args. So that's our argument of small a, where we set how many there will be, and semicolon of course e++, so that we advance to the next one. And here we will just let's say we said we want to add them all together, so we'll need a variable to hold it, sum, which starts with 0, and then we don't call this temp, but we just say sum plus equals this, and then here sum plus equals, and then we just repeat. So each time this is called, it grabs the next argument and assumes the type which we told it. And once we of course done, return our sum. And the specification says that we should use var and args, but if we go there, we see that this is pretty much a null operation. It doesn't do anything. It just assigns 0. I mean, it's not fully a non-operation, but it's close to. It just assigns null to this thing, and this thing here, as such, is just a pointer, depending on your compiler configuration. In our case, it's just a char pointer. So this already shows us that we could actually do already quite a lot without using this helper elements. For example, this var, when we go there, we see its implementation, so it checks and then advances the pointer and gives us. So here this is this plus equal, so this will advance the pointer and we'll get the value out of that. And then the next time we call it will of course be called the next time. So here let's use our function we already had. It has 10 arguments, and then let's pass the same arguments which we had already here, since then we don't need to type so much. Let's take a look how this will look. And as you see here, that's the release build, so let's switch back to debug build, which will be verbose and not optimize things away. As you see, it's pretty much the same thing, just everything is shifted by 1 since we have this additional argument. And when we go back here, then basically here we would have well, everything would be shifted by 1 upwards, and here we would have the count of the arguments, or rather this one would be like the and args, and so on, and the rest will just shift up. And this is why the calling convention was defined such that when a function enters, always there is this necessary space to copy those arguments, because if we are in such a variable argument function, we want to be able really to advance from one argument to the next, to the next, to the next, and not be like constrained that we can only start at the fourth argument or something. So this way, this initial space before the position where the function puts the return pointer is called a scratch area. So if you would be able to see some optimized functions doing things, then we would see that, for example, instead of decrementing the stack pointer or things like that, a function might really just use this memory for some computation and then return. So if you have very simple functions, then this scratch area might be quite useful, and of course it would not then just waste it with copying register content there and back. But with this variable argument functions, we see that this is actually quite necessary to have this, and of course we can try to implement this ourselves in a simpler way. So here, let's call it var2. We'll see if this will actually work out that easily. It must. So we just assume we have a int asterisk args is equals reference and arg, but this will of course be like the 0th one. So then we will, so here we'll still need to start at 1, because this we don't need, and then here this still is equals, and then just args from e, and this will give us the same thing, so we can compare whether this actually works. Okay, so we step over this. So the proper result is 2D, and our own implementation of the same thing, 3a. So actually there is some mistake with some offset. Let's see. We start at 1. Are we dropping it? Then we go until 10. That should be actually fine. We can compare both implementations to see where our mistake starts. Okay, so we will remove those breakpoints. So we are here, and it contains 1, and then actually maybe let's improve this so that it's more helpful when we got debugging int temp. We'll just first put it into temp, and we'll see it in the I think we probably are just have the indices wrong. Okay, so locals, zack. So we have in sum 1, temp is 2, 3, 4, 5, 6, 7, 8, 9, 0, and we are done. And of course this thing doesn't do anything, so I guess here we are going one too far. Obviously here we will start at sum 0 and temp 1, since wait, 1. Should we have started at 2? Let's see. So we take the reference on this thing. This is A. Memory. Zack. A. Yeah. So every stack slot, as we see here, is 8 characters in size. But of course here we are not taking this into account. So actually we need a int64. Then of course this will complain, but we can just force it. And then here we can just cast this down to an int. And then it will do the right thing. Okay. Okay, so the first one is 1, yeah, that will now be fine. And this is 2ds, the same thing that the other function returns. So we need to be careful. Obviously, we need to use the right type, but as you see, in principle, for this variable argument function, we can do the same thing that is done with this macros, just really by hand and with some proper type casting. And now let's see how this, and generally this function calls would look if we would have something of a different type. So for example, a double. So my double 1 is equals 1, my double 2 is equals, oops, my double 2 is equals 2. Okay, then we'll, of course, we'll need the double function, which, let's say, it will also return a double, maybe. My function d double arc1 and arc2. The function will be doing the same as the other one. My right is equals arc1 plus arc2, and return the right and small r, then we return that. Okay, and then we my double 3 is equals my func d, my double 1 and 2, 1 comma 2. Okay, we put a breakpoint, we run it. Oh, we forgot to return. Okay, and we forgot the breakpoint. Okay, so as we see here, it uses different registers now. This XM1 and XM0. But the way it will use those registers, so we can enable them here. Floating point registers, which what else do we need? That should be already enough. So let's see. Step. Wait, didn't we enable the right ones? Ah, here they are. The other ones are outward. So they contain those two values. And then of course the function is called, and then the return value will be that will be slightly different, because the return value will be in the same register as the first argument was placed. So the calling convention for a double return value is slightly different. And of course, if we would have now a function which mixes integer and doubles, it would adhere to the respective calling convention at the respective index. So to demonstrate that, how that would look, let's create a function that takes doubles and integers. Let's say int arg3 plus arg2 arg3 and then int arg4. Then we just add all of them together. 3. The compiler will take care for the right types. So let's call the other function with, let's say, 1, and we can actually use maybe those variables from here instead of literals. And this of course needs to be I think it was the I in the name. Okay, so let's take a look here. Right. Okay, and as we see here, so for the integers it takes the ones that it would take for the integers, and for the doubles it takes the ones which it would take for the double. So in this case, every second register of the complementary register set is not being used at all. And this is quite reasonable, because it allows you to have a reasonably simple structure of your code. So if you have, for example, inside the function, when we step in, we will also see that it is just taking those registers and saving them to memory. And this wouldn't work if we would have a variable argument function and then only 1 or 2 registers, and we would not know which the other one is at this level of the code. So then we would need to make everything much more complicated, and this obviously is not desirable. So that's how it works if you have different register sets which are used. It just makes a reasonable superposition of the two or more calling conventions which are being used in the system. Okay, this much to function calls. Are there any questions? No questions? Okay, we have about 1 hour left. So one thing that maybe I will still show you that is a bit funny about functions. Going back to this variable argument function. I want to show you that, or is that too complicated? In principle, it should be fine. There's one more thing that is probably interesting to see for you, that I will show you. So as we already have seen, we can create function pointers, and of course we can pass a function pointer to a function. So, for example, int my func do something, and this will take two integer arguments, like the other ones, and then it will take a function pointer. So int stern my func int. We don't need to provide the names here, it doesn't care for those. Okay, and then int that is equals my function, my arg1, my arg2. Oh, maybe my arg2 plus 2, why not? Let's make it less boring and return. And then we take our function. So my red equals something, small r. Then we take our standard. Let's just copy this wholesale. Then just reorder things. Zack. Okay, and voila. Now we will have a function that will call a function which we have passed to it as an argument. That could have been here as also a function pointer, so in any case it just generates a function pointer. So this is simple enough and does not require anything special. And this is actually quite a useful programming method, because, for example, if you would have a function which can sort lists, but you have elements in lists for which there is no natural order. So you need to provide a function which will compare two elements and tell the sorting function which of those is smaller than the other, for example. So in such a situation, you could use this method. Also, when creating threads on Windows, you are providing a function pointer to the function which will be the first function inside the thread, and one argument for it. One argument is pretty always enough, because you can just pass a pointer to a structure with arbitrarily many additional arguments inside. So it's rare to find mechanisms that allow you to specify more than one arbitrary parameter, as this is usually already more than enough. One notable exception here is the message system of Windows messages, in Windows, but this is more for historical reasons than anything else that it was made this way, and and that's that. Okay, so since we have functions covered, let's take a quick detour or a quick jump to the next thing that will be interesting. Memory management. So as we already have talked about it a little bit, I will create a new project for that. This can be closed. This can be closed. Create new project. Next, we call it memory. So as already mentioned, in a computer, the whole physical memory is in the physical address space, but all the applications which are running on your system, they only run in they only use the virtual address space, which is then set up by the operating system. The operating system as such can of course use the operating system kernel, to be exact, can of course use physical addresses and read and write physical memory directly, although this is generally not encouraged, since it is a bit error prone. So even in the kernel you will have, so when you write a driver of your own, for example, you will have mechanisms for proper memory allocation and memory management. They won't be as convenient as what you have in user mode. So as already mentioned, today in user mode in your application, The kernel 32 DLL will provide you with quite a few nice memory allocation functions and a application heap that you can use to efficiently manage memory without having to write this thing. If you are writing a driver, you can only ask the operating system for bulk memory, then you need to manage it yourself. You could, of course, just use such calls, but this would be wasteful. So pretty much any driver which does more than a little with memory will implement some sort of own custom memory pool. For most user mode applications, this is total overkill, so using the application's default heap manager is perfectly fine. And now we will take a look how this works. So we have our main function, and we have already included the Windows H. We could also have included stdlib H, but I like the Windows H more since it also gives us some additional APIs which are not part of the absolute minimum common denominator for all C languages. So if we want to allocate some memory in C which will not be taken from our stack, we use the malloc function. So let's define a function pointer, void my asterisk my memory1, and then this is equals malloc, and then how much we want, let's say 1000 bytes. And this malloc call will internally do a call to a heapalloc function provided by Windows. But for example, on Linux you also have a malloc function, but it internally does something Linuxy. So a good subset of things that you can do in C is part of the standard library, so that you can use it on Windows, on Linux. You just need to recompile for the targeted platform, but you don't need to change your code at all. And with the modern features in I think C20, you even get quite a few file system options in the standard STL library, but this library we'll take a look at later. So the STL library is for C++, while the standard C library, the C runtime, like in stdlib or stdio, is really just for normal C. It of course works in C++, but it can also be used just in C without the plus plus. So we can of course allocate as much memory as we want until at some point there is no more memory available in the system. And the important thing here to keep in mind is the two things. First of all, such a thing can fail. So usually you would want to check if it actually worked. So if, for example, this is equals null ptr, then let's say return -1. So we just return an error because, well, we should have checked all of them actually, but let's be lazy and just only check the last one. And such memory allocation, as said, might fail because you actually exhausted all the memory of your computer with too many Chromium tabs, or on a 32-bit in a 32-bit application there are situations where technically there might be enough memory available, but practically you still cannot get it. For example, so on 64-bit your address space, well, is 64-bit, which is huge, but on 32-bit your address space which is available for your application is only 2 GB, which is kind of half of the maximum address space of a 32-bit number. And if you request, if you have already requested a lot of memory and then freed it and then requested, etc., you might have memory in different places of your address space, and then if you want a larger chunk, there might be not enough consecutive unused addresses to satisfy this request. Even though there would be enough memory if you would request 2 smaller blocks, it might not be if you want it in one chunk. On a 64-bit system, the address space is so huge that the allocator will always find some memory where which is large enough to put whatever you have requested in. So in principle, you could request more memory than you have, and then it would only fail based on there not being enough memory available. Okay, so that much to this. So of course, the opposite thing of allocating memory is, well, freeing it. When you use the stack, this is kind of implicit. When you return from a function, all the space used has been released, and on the stack it always happens. It's like a stack. You put things on the top, on top of top, and then you can take them back again only from the top. On the stack you cannot like free some memory within it in the middle or something. That doesn't work. This you do with the heap, which you can use with this malloc function. So here, while we allocate it in the order 1 to 3, we can, let's say, I decide I don't need memory 2, so just 3, memory 2, and in this moment memory 2 is no longer used and available. Whether it actually would cause a crash when you try to access memory 2, that's a different story. Because as said, the internal implementation will get a huge block from which it will give you something, and if you ask again, it will give you again something. And if you then, in our case, say, okay, I don't need 2 can be, well, reused, then it will just mark in its internal bookkeeping structures that this portion is again free, but it will still be valid memory within your application and for what the operating system is concerned. Which is what makes memory bugs and memory corruption so difficult to track down sometimes, because you might have a pointer which points to some object which was valid in the past but isn't anymore, and then if you start writing to it, you will overwrite memory which now belongs to other objects which have been later allocated, and you end up with a huge mess basically. So this is just something that where one always should be careful. So let's make maybe some more examples. So let's for help, let's create some structure, or actually maybe we can just copy a structure from one of our earlier projects so that we don't need to type it again. Structures. Which one is a nice one? Let's just take the simplest one from the very beginning. This one. Zack. So we have our structure, and as said, if we allocate it normally, my struct on the spaces on the stack, we have a structure on the stack, and it will be there until the function returns, or if this would be in a scope, then technically until the scope ends. And if we want the same structure but on the heap, then we just make a pointer, and then we of course have the name on the heap, and then we just use malloc, and of course we need to tell malloc how many bytes we need, so we use size of to get oops, typo. And then of course it complains because the type is wrong, so we need to cast, because malloc always returns void asterisk, which can be pretty much anything. We need to tell the compiler, okay, we know that's a void, but it should be fine, so make a struct asterisk out of it, and then we can use it. Yeah, and of course if we would have a, so let's say it will be a p, because it's a pointer, and actually here we could also have a pointer, then p equals reference. And of course the important thing to keep in mind is that this thing, even if now it's a pointer and you could give it a function which might remember it and try to do something with it, but if the function to which stack frame this data belonged returns, then this memory will be invalid, while our heap allocated memory will be as long valid until some function somewhere at some point calls free. So and this brings us of course to the next good opportunity to screw something up, is if we now just return from the function those two memory blocks, memory 3 and memory 2, they are still there. They are not going anywhere. They are not disappearing. There is no mechanism in C++ that would detect that they can no longer be accessed, that they are useless. They will just stay there and waste memory until the whole application terminates. So when the application itself is killed, the operating system, it keeps an own list of what memory the application got, and then it will free everything. But obviously it's not desirable to have your application consume a few gigabytes of memory after a few hours of operation simply because it fails to free it. So it's important before you return to always, we need a return value. Let's 0. So it's important before you return from your application to free all the memory, so that there will be no so-called memory leaks. Oh, and of course we have one more we need to free, this one here. And the free function just takes a void asterisk, and any pointer is castable to void asterisk, so you don't need to use a cast here in detail. So to demonstrate this memory leak situation and problematic, let's just demonstrate it. with a function void my memleak. Oops. And this function will just let's say allocate some memory and then do nothing, and then we'll just return. And then we can have a loop, let's say here, for let's make a big loop, like a few thousand times. Int is equal 0 is less than a million I++, and then we call our function our memory leak. And when we run it, we should observe the memory usage. So we have here the memory usage of the system. It's a small VM, so it only has 16 gigs of RAM allocated to the whole machine. So let's run it. And when this runs and does something, we see here that it is rising, but then it finished and it fall back to 0. So actually we need an even longer loop. Let's make it not a million but a billion times. It will run 10 times longer and waste 10 times more memory. So we see it here. It rises also here. Isn't there diagnostic panel somewhere? Okay, maybe I have not installed this. But as you see here already, we are reaching the limits. The line is the amount that is physically available in the system. So at some point this will start crashing. Or actually, we managed to finish. Or did it crash? No, we did not crash. We managed to finish before before we ran out of memory. But obviously this is not something desirable. So you should not have a memory leak and just free your memory after using it. And now if we run the same loop, it finished, and as you see here, the memory usage pretty much didn't even spike because it only allocated a kilobyte at a time, which it then freed. So here obviously we won't see it with this resolution. Forget free on purpose. Okay, so that much to this. As already mentioned, you might have a limitation of how much space you can actually with the memory address space. So as said, this is only something for 32-bit, but it's something you might want to keep in mind because there are still a lot of 32-bit applications, so they can only use up to 2 gigs, and even if there is enough space, they might run out of the actual address space and not out of memory. Now we can also take a look on what we can do with special Windows functions. So let's comment out here our memory leak. So Windows, first of all, Windows has this heap-alloc function, which usually does the same thing as malloc. Actually, we should maybe step into malloc so that we see it. Malloc and free. Can maximize it here. Let's see, can we step into it? Yeah. Call stack. So here's part of the C runtime. Okay, first of all, malloc differentiates between malloc debug and malloc base. Malloc debug is like a special version for debug builds, which does additional checks. But since this is a debug build, it does this. So let's step into it again. That will actually take forever until we are where we want to be. We could run it in a release build, but then we will probably not see anything. But at some point, the thing will call heap-alloc. So what we can do, actually, to find this easier, is first we actually use heap-alloc here. We put a breakpoint on it. We find its address. Actually, we can move it on before. Heap-alloc. Let's say what we want to allocate. Well, null should be the application default heap. I think we are allowed to pass null. I don't recall, but I think that is allowed. Flag 0 and size 1000. Okay, so we put a breakpoint here. We enter the function. Okay, and this function here, RTL heap-alloc is part, in this case, of the NTDLL, so we can put a breakpoint here. Then we put a breakpoint there. it didn't like the null. So let's get was it default heap? No. Call the name of the function. There is a function to get the application's default heap, which is used. Let's see. Create heap, destroy heap. We can of course create our own heaps, but I want the application. It's called get process heap. This will give us the default heap for the application, and with this it should no longer crash. So we will run it. Okay. We forgot if you set a breakpoint on on something like the TDLL, for example, then unfortunately those breakpoints get cleared. So we need to enter our TDL function. And you see that the breakpoint here, it's like this empty because it's not active. Now it's activated, so now it should work. So now we run. And now when we make this malloc, I will put a breakpoint here. When we run it, we see that we have arrived internally before the other breakpoint here in the breakpoint on the NTDLL. And now we inspect the call stack, we see. So we start with malloc. Actually, we can go here. So we start with malloc. Then here we have this debug alloc. Then again here we call this heap alloc internal, which then is already quite complicated, but at some point it calls the heap alloc of the operating system. This would be much more streamlined if we would not be using the debug heap and running in a release configuration. So internally, as said, this maps to this Windows functions. And what we also can do is, which is quite a useful trick, is we can create our own heap. One which is separate from the application default heap. So we need a handle to it. Equals heap create. Option 0. Initial size 0. Maximum size 0. So we don't care. We could specify some limits here, but we don't care. And then of course if we use our heap alloc, we would now pass this heap instead of the other one. Void memory4. Decapitalized it. I called it my memory, so my memory4. And now we could of course either just free it. So free resolves to heap free, which takes the heap on which the operation has been performed. And of course the normal free will just default to a heap free call with the application heap as a first parameter, and flag 0, we don't care. And we provide them. And the nice thing about being able to create an own heap is that instead of freeing everything that you have allocated on the heap, you can just heap destroy. And then just provide the handle to the heap, and this will just release all the memory that the whole heap has allocated. So every heap alloc from this heap, every memory that this pointed to, will become invalid. So we can actually put a breakpoint here and a breakpoint there. Let's see. So we have here our heap. We can take a look what's there. As we see, it's this my memory was not initialized. We could specify different flags for this heap alloc. So I think there's also one that actually makes it initialized with something, but here it just contains something not important. And when we do this heap free, as you see here now, the ID shows question marks, which means that this whole memory range is now invalid. And this basically is what happens. So you don't need to. So if you know that you will be allocating some memory and you want to save time on cleaning it up, you could actually create an own heap, use heap alloc with that heap, and then instead of freeing every single thing you allocated, just destroy it all at once. This is quite a useful trick. So yeah, as long as you avoid creating memory leaks and or accessing invalid memory, that this is all really nice to use. We can here, if you want to initialize it, I think, what was it, heap heap zero memory, yeah. So if we would run it with this, it would not contain garbage, but would only contain 0. So there are a few flags which we can use. What else we can use? We can like reallocate in place. We can do a few things so that it is quite flexible, but I think demonstrating that is not really necessary. What the compiler does in the debug build, actually, with one of the functions when we see here, is also quite interesting. The heap memory is initialized. So if you use malloc, the memory will be initialized to CD, 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 and so on, and indicating that it is uninitialized memory. And if we then, let's say, we take a look at memory 2, we have not allocated memory 2 yet, so we step until we have allocated it. So it has this CD, 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 and here we have a free call. So once we execute free, as you see, the memory is still valid because it's not, it doesn't show question marks, because it only marked it internally as free. It did not tell the operating system to get rid of it. But the debug heap has overwritten the whole value range that belonged to this memory block with the DD, indicating that this memory has been deleted. And of course, in the release build, it won't initialize it with CD, and it will not overwrite it with DD, because it's kind of unnecessary. If you allocate some memory, you want to write your data to it, and if you free it, you are not intending to read it anymore. But in the debug build, this is actually a very helpful mechanism, because if you would try to, for example, read a pointer from this memory or do something with it, you would quite quickly either cause a crash or at least see, based on the values, that you are reading something that has been deleted. So instead of reading all data and garbage, there is a good chance that you will actually notice that something went wrong, and before like the memory got corrupted so much that you won't be even able to debug it why it happened. So this is something which is quite nice. And if you have all this debug features enabled, which we usually turn off, you would see, for example, this thing here. When we go there, well, we are not so far yet. Let's put a breakpoint here so that we actually can go there. As you see here, this structure which was created is also pre-filled with a pattern, but instead of CD, it's pre-filled with CC. So like if it's memory on the stack which is empty, or rather uninitialized, it's pre-filled with CC. If it's something from the heap, it's pre-filled with CD, and if you free it, which only applies to the heap, it will be overwritten with DD. And when we take a look in our main function at the beginning, here is the code somewhere here, this much, somewhere this much, which actually overrides the whole stack frame of the current function with CC, such that we can easily notice it. So you see it exemplary here, that really the debugger generates extra code to help us debug issues. And if we of course turn off this runtime checking and stuff like that, then this will of course then behave differently, and we will not have this code. So if we, oops, that was the wrong button, I have to stop it. If we go here, code generation, basic runtime checks, and disable this, oops, that's completely. Then we run it again. Let's put a breakpoint somewhere at the beginning. Then you see here this code is no longer there, and if we go, how far do I, far enough, here, and then take a look inside the function. Oops, I pressed comma. So the function, it's actually ended up having zeros, so it's not completely bad, but as you see, it was not initialized to anything meaningful either. So in release builds, it is much more difficult to track down such memory problems. Debug builds, on the other hand, are usually extremely slow. So there are different and they use also more memory. So for example, that in the memory manager in a debug build, if you ask it for a memory block, we can try this actually as well. It will give you that memory block, obviously, but it will actually reserve for you a significantly bigger block, maybe not significantly, but noticeably bigger block, and put a recognizable pattern before it and after it. And then when you say you want to free it, it will check whether this pattern is still there, meaning that you have not exceeded the amount of bytes writing, for example, to it that you were allowed to. So let's say we stick with our memory 1 here before we free it. For e is equals null, e is less than 1000, e plus plus. Memory, let's say it's a char asterisk, oops, at e is equals e. We just, I mean that will not be able to count up to 1000 because the char is less. So effectively it will do a modulo this. It will just truncate the bits, but you know, why waste CPU cycles if the result will be the same. So let's just put a breakpoint here, run it. First inspect our memory 1 in here, so go up. Okay, we see that before the CD there is some FD pattern, and afterwards, go far enough, there is another FD pattern, and then some zeros, and then some other stuff, and something that apparently already has been deleted. So this will probably be our memory 2, which we have already deleted by now. It's now filled with DDs. And then we have another CD, which probably is the next memory block, our memory 3, which we haven't used yet. Okay, and if we run this and put a breakpoint here, it's all happy. But if we try to write too much, let's say 1 byte too much, then in the release build, the thing, once we run it, should not be happy. It's loading stuff because it wants to show us a window saying that something bad happened. So it's not necessarily the nicest thing that it loads all the graphical stack just to tell us that it will now crash because of something. Just issuing a interrupt and invoking the debugger would be just as good, but that's how the C runtime of Windows is written. So since we have not done anything with graphical stuff on this VM yet, and we have enabled symbol loading, now it will need to load all the symbols for the DLLs, which now will be needed. And apparently there are many. And we have our crash window, so debug error, program such and such, heap corruption detected, very bad thing. After normal block number so and so, at address such and such. And now, in principle, you could press retry, which would bring us inside the debugger to the place that crashed. Okay, now it wants to load some more libraries. Let's wait a second. The other option would be ignore, which would kind of gracefully continue, or abort, which would just crash the application, and that's that. Okay, it's still loading something. It's loading, so it's loaded. Well, it's still crashed. The problem is that when it so if we just press on cancel, let's see if we get a better result. Normally the repeat should bring us in the debugger to where that happened, but for some reason that doesn't work right now. Just it just trapped in the message loop of the message box. It doesn't exit that. So there's something broken. One thing we could do in principle, we could disable the the symbol loading. That might speed up things. No, we have to disable this from the tools menu. Okay, so Yeah. This should not load then symbols for everything, but I don't think it will help us. It will still be broken, which is a bit annoying. Always using the newest version is not always the best thing, but generally the idea is that it finds such errors, and then if they happen, then it will in some way notify you about that something bad happened, and then it would be crashed. If it would crash, if this would be a release build, you could just overwrite this part of memory, and it would not notice that there is anything wrong with that. And there are similar guard mechanisms placed around your code in a debug build in different other places as well. If you have not disabled, as we did, this checks here, basic runtime checks. The heap checks are separate from those, so they trigger even if those have been disabled. Okay, and since we are already approaching the end of our time for today, I think it's a good time to give you some homework. So this memory management, since we just started it, we will just leave as is. Structures I can close because we don't need it. But with functions, I think it would be a very good exercise to write a few functions of your own. So from the 03, 04 to 0 to 5. One. Calculate the average given of numbers. So let's say double calc average size t count double asterisk array. Okay, so this one takes a array of doubles with count entries and calculates the average. So you sum everything together, divided by the count, done. Then let's do something more advanced. Calculate standard deviation. And since for the standard deviation you need to have the average, you can have here a optional parameter double Stern AVG output. Oh, and there is one thing I forgot to tell you about functions, which is also quite nice. You can specify, let's do it with this function, you can specify a default parameter. So you can write it like this, but this works only with the last argument. So you cannot have a default parameter somewhere in the middle. Just from the back you can fill up your arguments with this default with any default parameter. And then when you are using the function, you can just omit specifying them. And when this compiles, the compiler just looks up what is the the default argument for your value, and then takes it and puts it in your code where you knowingly omitted it. So here we will do it the same way. So the standard deviation function, of course, is better. Then we could, of course, have a integer function like find max, which takes let's say similar thing just with integers. Well, and find mean, obviously. Then we could do the same with the variable argument functions. Argument function. Okay. Now there will be much more other funny things with functions that can be done once we start the C++ portion of the course, but for now I think this is already a good early beginning into using functions and function calls. I'm thinking if I can think of something which would be simple enough that you could try recursion, i.e. when you have a function that calls a function that calls another function. Oh, and by the way, for the standard deviation, you need the square root, I think, and that's not super easy to implement. But there is the MathH library, which provides a huge amount of really nice functions. So like power, so you can already take something to the power of something. Here it's with doubles. You can use SQRT, square root, just from something. So actually, this is it only? No, it should be implemented for more than just one type. Yeah, it's implemented for doubles and for floats. Depending on the preset, you might also find some which has int_x implementations for just integers. But I think we don't have that here. I don't know. It's a very simple implementation. Just use these doubles, and it will just cast the value even if you provide an integer to a double and then pass the double as a argument. So you can use that for integers. But for integers, we only have the find, min, and max, so there you don't need mathematical functions. And this MathH has quite a few. There's some sines, cosines, calculations, everything you might ever need in a simple program. It of course cannot do any more complex stuff like matrix operations or vector addition and stuff like that. It's really just the math operations for scalars. But there's a typo. But you can, of course, write some own much more complex libraries or use third-party libraries for math. There are more than enough libraries, some even from Intel themselves, which allow you to do matrix mathematics and other and linear algebra and everything you might ever want to do. So it's just if you see something that is a bit more complicated than what you would want to write yourself in a few spare hours, then you just look for a library. And generally this is a very good advice, I think. In the world of open source, there have been so many things already done that even if you are a young and motivated person thinking, oh, I'll do everything myself, I'll write everything myself, that's a waste of your time. Just look for something that has already been done that does this and include that library. If the license permits, obviously. But in our normal scientific use cases, everything that you will find in the open source world will be at least GPL, which allows you to use it for anything as long as you make the sources available. So for such use cases, this is just fine. If you have such a program, then you just put the sources on whatever data repository your research group is using, and then it's perfectly fine to use whatever you want. And of course, many other things licensed under LGPL, MIT, BSD licenses, etc., are more permissive. So you can even create a commercial product using those with only very little restrictions. Technically, you can also create commercial products using the GPL, as all the companies that are selling Linux, like Red Hat, are doing. Just that you have to give the source codes, which means you cannot enforce any additional license terms, meaning you have to rely on people buying from you because they want to support you and not because they have to, because they don't. They can just download the code and compile themselves. So that's the main limitation of the GPL with regard to commercial use, that you cannot enforce anything. I think that was enough for today. During the next lecture, we will take a look on strings. So as you might remember from variables, I already mentioned that strings are represented as arrays of characters, but there are quite a few helper functions, like math here. There is also a strings h, which contains many helpful helper functions to work with C-style strings. But we'll also take a look on other string basically the many different ways how you can make a string from what the CPU allows you to do. And once we're done with that, the last very low level thing will be the exceptions. I think we will do it the next time as well. Also, when we will be doing strings, we'll take a look on writing and reading text from the console, and maybe writing and reading some files. So this will be most stuff that belongs together. And then we will also implement some sample a more complex sample application, at least sample functionality using just C. And after that, we will move to C++. So it will be getting very exciting very soon. And that's that. So have a nice evening. We'll see each other next week, I think. I think the holidays start the week after the next week. So with the homework from today, you already have time to until after the holidays. So no need to hurry. On the other hand, if you want to have free holidays with a free mind, then maybe you should hurry and do everything before the holidays start, so that you can enjoy your holidays without any pending work. Yeah, that's that. So let's see each other next week. Bye bye.